Wear debris analysis compared to spectrographic analysis. The majority of oil samples from machinery are analyzed and monitored by spectrographic analysis. This presentation displays the limitation of spectrographic analysis when compared to wear debris analysis by microscope. Spectrographic analysis, ICP or RDE. Spectrographic analysis is the usual routine method for plant and equipment lubricant condition monitoring. Method principle ICP, induced coupled plasma. A solvent-reduced spray of the oil sample is injected through an argon gas ionized plasma torch, creating a high-temperature plasma, approximately 8,500 degrees Celsius. Method principle RDE, rotating disc electrode. A high-voltage discharge arc is applied to a porous carbon disc rotating in a small portion of the oil sample, inducing a plasma-like state. Induced coupled plasma spectrographic working principle, ICP. The ICP spectrographic analysis works by the first system sample introduction. A robot sampler picks up the sample from a test tube. There could be 100 samples in the grid. Peristaltic pump moves it through the nebulizer in the ICP system. This sprays into the plasma torch, which excites all the electrons. Ion lenses focus it in the plasma sampling interface. Then in the mass spectrometer, the filters split the sample up so the detector can determine what elements are present. Usually there will be a detector for each element. These measurements are displayed as the analysis results. Optical emission spectroscopy using a rotating disc electrode, RDE. This is a more manual system with the electrodes loaded in the system individually. The electrode, which has been soaking in the sample for a predetermined period, rotates in a sample cup of the oil. A fixed electrode supplies the arc to produce the plasma dot. The optics and diffraction grating produces a spectrum, which are displayed as the analysis results. Analysis process for both ICP and RDE spectrographic. As the sample passes through the high-energy plasma, electrons from the different elements in the sample become excited. When these excited electrons return to a lower energy level, they emit light that is characteristic for each specific element. The emitted light is measured by a detector. This measurement provides a determination of the elements present in the sample. The results are typically reported as parts per million or ppm for each element detected, such as iron at 35 ppm or copper at 60 ppm. Spectroscopy limitations. Particle size limitation. Both ICP and RDE analysis methods are size limited. They can only vaporize and detect particles up to 10 microns in size. Particles larger than 10 microns cannot be fully detected and are usually invisible to these analysis systems. Application differences and detectability. Engine applications are often well filtered. Wear tends to produce smaller particles first, allowing spectrographic analysis to detect and trend abnormal wear. Gear drive and transmission applications wear differently, often producing wear debris larger than 150 microns. Particles larger than 10 microns have too much mass for spectrographic analysis to vaporize and detect. Consequently, spectrographic analysis results may not reflect heavy abnormal wear conditions accurately. The following examples indicate the limitations of spectrographic analysis when monitoring transmissions, gear drive, and hydraulic applications. The left-hand images wear particles sized at 6 to 8 microns would be detectable with spectrographic analysis. The right-hand images larger particles may not be detected accurately. The images below display 3 concerning abnormal wear modes that could remain undetected for up to 6 months before the metallic wear debris becomes broken down small enough for spectrographic analysis to detect. These samples have been analyzed by spectrographic and microscope wear debris analysis. On the left, we can see the above ICP spectrographic analysis results are all reasonably normal. But when we check below, the WDA by microscope has detected bearing spall and steel fatigue wear debris requiring an oil change. Note how these particles were not detected in the ICP results. On the right-hand side, the above spectrographic analysis are all reasonably okay. When checking the oil sample with the microscope, we can see there's heavy bronze abrasive wear that requires an oil change, displaying the difference in detection limits between analysis. Spectrographic instrument particle size detection limit, less than 10 micron, can miss more serious wear modes. Even with spectroscopy, particle counting, and PQ combined, recommendations may not be acted on because there just isn't enough information to justify changing procedures. Analysis of oil or grease samples via wear debris analysis by microscope provides information on wear modes and contamination types far more accurately than methods like ICP or RDE spectroscopy. WDA by microscope root cause is the reason for the contamination found. Identifying the contamination allows proactive steps to remove and prevent recurrence. WDA by microscope restores applications to target cleanliness levels significantly faster with fewer unnecessary oil changes compared to relying solely on ICP or RD spectrograph results. Note the three images on the right. The microscope has root cause the haul truck centrifuge cake sample. The top image displays silica crystals. The engine has been dusted. The middle image is large chunks of white metal embedment layer. The silica crystals are abrading from the bearings. The lower image displays the fine dirt is causing arcing in the engine's bearings, producing these carbonized lubricant particles found in the sample. From the information gained through microscope analysis on the centrifuge cake, the recommendation to the equipment owner is to see if air filtration can be improved. This analysis displays how new engine oil filtration removes all abnormal wear debris, and the best method to detect abnormal wear is to analyze the oil filter media or centrifuge cake.